Good morning, everyone. Hope everyone's had a good week so far. Also on some good topics and presentations. So the good thing is they saved the best one till last. Hopefully you're going to enjoy this. So welcome to my talk. We're going to talk today about how you can improve developer efficiency using some of the things that are in Unreal 5.4. We're going to look at some of the things that are up and coming as well. Incidentally, how many people here have seen some of my talks before, at Unreal Fest before? That's good, because I'm going to take it back again. I'm going to talk about some of the topics again. So the people that have seen things before, there will be some repetition of things that we're going to talk about. But the good thing is we're going to go from right back from the beginning all the way to where we are going to go in the future. So I'm director for the foundation group at Epic, and our kind of real main focus is on improving developer efficiency and developer iteration. And we're doing this in three ways. We're looking at how to accelerate data syncs, how to get data to people really quickly. We're looking at all the ways that we can reduce some of the real big blockers for you, things like how long it takes to build code, how long it takes to cook content, and how long it takes to even deploy a build to a target. And we're also looking at that target iteration loop as well, being able not just to be able to iterate in Pi, but being able to iterate on target as well. So the talk's split into two pieces. We're going to talk a little bit about what you can use today, what you can try in Unreal 5.4, and then we're going to look at how that builds on that in the future. So at Epic, we have three levels of release status. So experimental is we've basically just dropped the code in. You can take a look at it. We want your feedback. There's some of that code may change. Some features may get removed. We've got beta, which is essentially that Epic is using that for production. So we're probably using this on Fortnite or across a wide range of our products. And then finally, production is where you can absolutely rely on this thing being completely 100%, well, 100%-ish robust. And you can use it for your own production. So I'm going to use the experimental, beta, and production ready throughout this presentation, just to give you some expectation of what stage that technology's at. So the first thing we're going to talk about is derived data cache and how important this is to developer iteration. So the derived data cache, it's one of the most impactful things that you do one of the most impactful contributions to poor developer iteration and poor developer efficiency is building things locally. So, you will load the editor, you'll open a texture. When you open that texture gets transformed into a binary representation. It'll be for the platform that you use. So if you're on PC, it might be a PNG at source, and then it gets converted to a DDS or something like that. That happens every time you load something. And we have the derived data cache there, and the idea of that is you only build that thing once. So next time you boot the editor, or you cook, or you stage, we don't do that work again, right? Now, that particular piece of that transform affects so much stuff: editor loading, cooking, package turnaround. And really what we want you to do is only build that one piece of data, that data once, right? So if someone else on your network's already built it, or you've already built it for another project, why are you building it again? And so the really important thing for you to get set up, if you haven't already, is a shared DDC. Hopefully everybody uses a shared DDC if they're on site. Does everyone use a shared DDC? Good. Now, the problem with the sort of legacy or the current version of DDC, it's file-based. And the file-based kind of DDC is pretty inefficient. If you cook or you build an editor, you just generate loads and loads of loose files. And accessing those files over just normal file system is pretty inefficient. So what we want to do is we want to move away from just reading and writing millions of loose files and sort of take a leaf out of a database modeling, model that data in a different way. So we've introduced for 5.4, it should be on by default, this piece of technology called an Unreal Zen server. And it's a service that can run locally on your machine. You don't have to think about it. Creators don't have to worry about it. It should be spun up automatically. The editor looks after the lifetime of it. And it's got a code base. The code base is kind of separate from the engine, so it's not got all that heavyweight engine code, and it's pretty lightweight. It's been written from the ground up to be really high performant. So the first use case of the Unreal Zen server is for your local DDC. So I said this is the thing that should be out now and you should be able to use. First thing of all, by default, it's shared. So if you've got multiple workspaces on your machine, and you've got multiple projects on your machine, out of the box, you get a DDC for each of those. You get all these extra files, all these files all over the place. So the first thing it does by default on a user's machine is it will share that database. So if you've built something for one project and it's the same for another, you'll reuse it. So we get full deduplication. We're no longer doing kind of bound by I/O. So we can do some clever stuff, like we can take, if you've got lots of really small files, we can coalesce them, and you can access them in line. If we've got really large files, we can split them up. So really, we get a good control over how we access that data and how we present that to the engine. And that makes quite a bit of difference in terms of performance and I/O. Not only that, we can also access data in parallel. We can asynchronously load data. So there's a lot of improvements there we can do to kind of that underlying efficiency. It's not night and day. I'm promising you that you won't just switch this on and suddenly see a massive performance improvement. But as you'll see, we're going to build on top of this technology, and this will give you, at the end, hopefully you'll see how this all fits together. So we talked about shared DDC. And for shared DDC, again, we want to get away from that millions of file problem. Normally, you'll probably have DDC on a network share. And if you're accessing that from multiple machines, again, there's a lot of chatty network traffic that's going on there. And being able to kind of decouple us from the I/O means that we can, again, do things like do async operations. We do parallel gets. We can do partial gets. We can organize the data in a much more efficient way. So getting that data from a shared DDC is also something that is, again, a lot more efficient. And then this is probably just, within a studio, that's normally enough. But, today games and the way they're made is changing. We've got a lot of people that, actually, quick show of hands, how many teams here are fully on site? And how many teams are, guess hybrid? The rest is basically all, I assume the rest are all hybrid, or everyone's just working from home, right? So how many teams are hybrid? Yeah, quite a lot of them. So this is an important part here, because you can set up a shared DDC and you can have all your studio on the same network, and that can be fairly efficient. But what do you do for people that are working from home? So Unreal Cloud DDC is essentially, you can think, although I'm not telling you this, you can essentially think of this as a kind of cloud version of Zen. So all of the APIs essentially that we put in the Unreal Zen server, we're going to be putting in this cloud layer. And the first one that we've shipped is the DDC, because the DDC is the most critical part of the process. And what we can do with Unreal Cloud DDC, we can just set a single instance of this up on the public internet. And it means people in the same region. So if you're in, let's say you're in Stockholm, and you've got a lot of people in Sweden that are all, that aren't sort of too far away from you, but they're outside of the office. Having a single instance of Cloud DDC allows the remote users to get good, efficient shared DDC. So they're not booting up. How many people here, when they boot up from home, take ages to boot the editor? Loads of you? Yeah? So a lot of that is to do with the fact that you're building everything locally. So a good shared DDC actually helps with that. A lot of people working from home, they'll be able to boot editors, they'll be able to cook locally, they'll be much more efficient. And then the final piece of the puzzle is teams are also geo-replicated. It's not just they're in one region. A lot of teams now have outsourcing, or they just employ people from all over the world. And so you want to have that same experience wherever you are in the world that you might have if you're in the studio. And this is where the next part of Unreal Cloud DDC comes along, which is replication. So at Epic, we have 5 Unreal Cloud DDC instances around the world. and they're doing active and passive replication. They handle things like OIDC login, authentication. You auto-connect to the closest region. Again, you're not building data that's already built. If someone on your network, whether that's a build machine, the other side of the world, or someone else has just booted the editor in America and you're in Sweden, you should be able to use that data. And the Unreal Zen shared server is optional as well. I mean, you can if you set up a shared, like I showed you on the previous slide, if you set up a local DDC in Studio and a shared DDC in Studio and then a cloud DDC, it may be that it's definitely should be faster to reach that cloud DDC than it is to reach the shared. So it isn't a requirement to have a shared DDC, but it is useful where you need a really tight, close, high performance DDC on site. So things like build machines will use this, or your developers on site. When you boot editor, we actually do a latency test, and we'll test we'll test which region you're in, and we'll test latency to the closest cloud instance that's in your region, and we'll also test latency to any shared DDCs you have as well. So sometimes it can actually be quicker to go to the shared DDC that's on the network. It really depends on on how far away you are from the kind of regional replication or from the local shared DDC. So it's completely behind the scenes. You don't have to go to each developer and set them up. It should be able to automatically route between them. So this whole model is how Epic works. We have that Unreal Zen server as a local DDC. We have Unreal Zen server as a shared DDC, and we heavily lean into Unreal Cloud DDC as this distributed shared DDC. And this model I want you to take away, because this is key to how we're going to build on this for the future, how we're going to improve a lot more things than just DDC for you in the future. So I'm going to talk a little bit more about another feature. So this is cooking to a Zen server. So we talked about DDC in the Zen server, but we can also store cook data there. So again, this is your legacy cooker, lots of loose files. You've got your DDC in it, but you can also put your cook data in it. Every time you cook, there's a save data. It puts save data folder. There's assets that get thrown in there. The cooked assets get thrown in there. Again, millions and millions of files. If the same cooked data is on multiple projects or multiple platforms or multiple workspaces, there's no deduplication when it's all file-based. So, the DDC and Unreal Zen server is underneath it has got a content addressable store. So, we can get full deduplication of not just DDC data, but cook data as well. And all the same things apply. The ability to share it at studio level, the Unreal Zen server. Ability to share it on a cloud layer, we can use the Unreal Cloud DDC or a variant of that. So I basically told you the next slide, but that's basically it. We remove all of that loose file stuff and put that into the cooked assets into the server as well. So again, not necessarily night and day, but some of the same things do apply here. So things like there being a less chatty protocol between them, being able to deduplicate, being able to access the data asynchronously, and being able to split the data up depending on its size as well. So that's cooking to Zen server, sorry. Now we're going to talk about how you can speed up cooks just in general with multi-process cook. How many people here are using multi-process cook? Okay, you should all be using multi-process cook. Well, most of you should be using multi-process cook. There isn't really a prerequisite. It isn't tied necessarily to things like, Zen server or whatever. It is something that you can use even without using that. But essentially, we're taking the cook graph, we're chopping it up into pieces, and we're cooking it in parallel. So it's not on multiple machines. This is just all in process, and we're trading CPU cores. If you think about cooking, there's quite a lot of the cook process that is single-threaded. It does go wide in a number of places, but generally there's just, it's bound by this single thread, and that's kind of its limiting factor. So it seems like a very obvious thing to split this up into multiple processes and have them run in parallel. So yeah, you are trading your local memory for reduction in wall time. It's not applicable to all projects because that whole process of the graph analysis, splitting it all up, and then sticking it all back together again. You have an epilogue and a prologue that they're non-zero. So for small projects, you might not get a massive return. For larger projects, you should definitely try it. So multi-process cook takes that graph at the beginning, what we would have done in one big long list. It splits it up. It does graph analysis. It looks for where it can chunk things up based on loads. So you're not loading data that you don't use. So we're trying to portion that stuff together so that we get like the most efficient use. We do sometimes overcook on these processes. Why? And some of that reasoning is why we don't get like 4 processes give you 4x. It's not linear. It certainly isn't a linear relationship. And we're also, the system's also able to retract tasks as well. So, if one of those cooks, because at when we kick this thing off, we have some idea of how long the process will take. We try and divide the graphs up evenly, but the devil's in the details. So you can sometimes find that there is a long pole, but we do have task retraction. So in general, the cook workers tend to finish roughly around the same time. So in terms of what the results were, on Fortnite, we had a 2.5x improvement with 4 workers. So this says December the 2nd. So that's not December the 2nd, 2023. We switched this on at the end of the year in 2022. So Epic have been using this on Fortnite for a whole year. So it's completely battle tested. It's made a massive difference to our turnaround times on getting builds, and it's ready for you guys to use today. So give it a try, give your cook times a boost. It's just a couple of switches and off you go. So you can try more processes, but it's diminishing returns. So this 2.5x with 4, you don't get a 5x if you have 8. It doesn't work like that. But as I said, you start getting into the thing where you're kind of multiply cooking the same thing in different processes, or you're getting I/O pressure and you're getting additional memory pressure. So your returns will vary. Who knows about virtual assets? Good, not everyone, so that's good. So virtual assets is a way of really trying to reduce sync times, right? So if you take a look at an asset, it's made of 2 pieces, the DNA of it, 2 pieces. There's what we call the structured part, which is essentially the properties and the structure of the data. And then there's typically inline bulk data. Now, what happens when you load your editor is that you load that structured data, and then you look at it and you go, oh, I've got this bit of binary, I've got this pixel data, I've got these settings. You go and have a look in the DDC and you go, given that I've got this pixel data and given I've got these settings, do I need to rebuild this? Well, this is where the key piece comes in. With a shared DDC, if someone else has already loaded that texture and they've already created that DDC, then you don't need to process it. If you can get the result in DDC from a good shared DDC, so you don't have to process it. And if you don't need to process it, why the hell are you even syncing that bulk data in the first place? You don't need it. You only need that bulk data when you actually change something within the structured data. So what we do is we take regular assets, and as a pass, you can do this retroactively as well. You don't have to, like start with new assets. You can go back over your entire existing content. You can convert that. We've got tools for you to convert it. And what you do is you split that bulk data from the structured data. So structured data, what's in the U asset is essentially the structured data and a hash to that bulk data. We take that bulk data and we store it in 2 places. We store it in Perforce in a common folder. And this is really about making sure that we've got a copy of it, because the other place we store it is in the DDC. And obviously the DDC is a cache, and caches invalidate, caches go out of time. If we've got any kind of cache pollution, we don't want that primary data getting corrupted. So we always store a backup of the bulk data in Perforce. But not only do we store the output of that texture in the DDC, we also store that bulk data as well. So more often than not, someone will sync up a virtual asset, they'll load the editor, they won't need the bulk data because it's already in the DDC, and that DDC is already shared. And if they do make a change, let's say they change the sRGB flag, and that means that the texture needs to rebuild. At that point, they need the bulk data, and we will go to the DDC first before we hit Perforce. So you're actually in the situation where you actually need the bulk data, we very, very rarely touch Perforce. We only touch Perforce if we can't get to our DDC. Did I talk about size? Yes. So what I didn't talk about, which is on the slide there, is what big difference it made. So we were able to reduce the size of Fortnite's content from about 400 gig to 125 gig or something. So a 4x improvement. And that makes a massive difference. If I work from home, and for the first 18 months of me being Epic, I couldn't sync up to Fortnite because it was too big. It would take overnight. Now I can sync up to the latest build of Fortnite. I can do that within about half an hour from home. So that the proof is in the pudding there with that. So this is all good. This is again if this is production ready. We've been using this for 18 months again, nearly 2 years. We've been using this. So it's all ready, and if you're not using it, use it. But, as I said, it does really rely on you having a good shared DDC, because if you don't have that, when you have that cache miss, you end up going back to Perforce and pulling bulk data one at a time from Perforce. So here's an interesting new piece of technology, which I don't know has anyone heard of Unreal Build Accelerator? Yeah, I thought they might have done. So UBA is an out-of-the-box solution for distributed compilation. And, it's Epic first. You can have all the source code. It's completely supported. We use it at Epic for 95% of our compilation builds today. That's local compilation, build farm compilation. The only places where we don't use it is where it's not supported by legacy. We've still got a few builds that are built in Unreal 4 and so on. So those builds use other systems to do their compilation. But everything else at Epic is using UBA. And UBA, although you can use it outside of Horde, the way that we are releasing it for 5.4 is that you use Horde as the remote execution broker, essentially. So you use Horde's remote execution system. It doesn't mean your team has to convert over to Horde. If you're already using TeamCity or Jenkins or whatever, that's fine. Carry on using it. You can spin up a Horde server and just use the remote execution part for this. And this is really, really cool. So how does it work? So when you do a compilation job, UBT, so UBT, Unreal Build Tool, will go off and talk to Horde, and it will say, give me some compute resource to run my compilation task. Horde server has a bunch of agents. It allocates an agent, and then it tells UBT, here's the list of agents that I've allocated for you. UBT passes that on to UBA, Unreal Build Accelerator. Unreal Build Accelerator is a separate program. It doesn't, it's not embedded into UBT. It runs separately. But essentially what you do is UBT, you get these, bunch of remote workers back, and then UBA is told about that list of workers. And what it does is it uploads itself first to each one of those workers. It's a tiny little program. And that means that if you're using a different version of UBA, you can be sure that the remote workers are all using that same version. So that's the first thing it does. And then UBA from then on, UBA talks to UBA. It's got a list of all of the workers all of the workers that are remote, and it's got this one UBA instance that's local, and that local UBA instance is the one that's kind of responsible then for scheduling all the work. So yeah, essentially, Horde's like does the introduction, and then UBA does all the rest of the business there. So in terms of results. So you can see when we switched it on, that was August last year. So we've been using this almost a year now, UBA, in production. That's where we switched it on last year. We saw almost a 3x improvement in build time over what we were currently using. So 15-minute pre-compiled binary editor jobs down from 15 minutes to 6 minutes. So pretty impressive stuff for something that you get for free. So for beta, we're doing a limited release for beta, and I want to be clear about what to expect for it. So for beta, it's C++ only compilation on the same physical network. So that is, you'd set up a Horde server, you'd install some agents on some machines, you configure UBA to talk to that Horde server that you've set up, and you configure those agents to do some CPU control locally, and then you can go away and build all your C++ code. You can use it, and when I say local network, that could be, you could just have a bunch of machines at home, and you could set UBA up, a Horde server up at home. And that's how, when we first started testing, that's how people were really getting along with it. They had these machines sitting around, they just span up a Horde server on them, and then use those as agents. They set up a Horde server, use those, like, people using strange things like Raspberry Pis and all sorts for it. It's because it's so lightweight, you can spin it up on a lot of different things. But if you've got a lot of machines like kicking around at home, and they don't even, not even work machines, you can set up a Horde agent on those, and then, use a shared server, and then distribute from home. So that's a good solution just now. If you're working from home, you can use it. And then obviously, if you're in an office, you'd have a single Horde server set up on your network somewhere, and then, you could dedicate a whole bunch of machines to it. It does work over VPN, but at your own risk, basically. The throughput over VPN, the fact that VPN's quite high latent, and you've probably got a load of other traffic going over VPN as well. This is quite, the amount that you can shove across to UBA is huge. So, you could actually end up crippling your VPN if you start using this massively for compile jobs. But they're all things you can try out. It does work on the cloud as well. Again, it's not something that we're talking about for 5.4. But you can set this up on the cloud. You can set up cloud agents. As long as your Horde server can register them and can access them, you can have this doing cloud distribution. So some of the limitations, you can only really use it on dedicated helper resources. So, you can't just go and install this on a bunch of artist machines and then go and steal all their CPU time. But you will be able to in 5.4. That's the good thing. So, so at least for this release, if you've got a fleet of machines that you can use that aren't doing any other work, if you're using other distributed compilation systems, then there's no backing off of a Horde agent at the moment if it notices a certain process. But we will be doing that as part of 5.5. So there's a lot to try. We'd love you to have a go of it. You can definitely get some value today from UBA. Hang on. Okay, there we go. So what's in the box for 5.5? Working from home solution. So I'm here today. I'm in Prague. I'm compiling Fortnite editor on my laptop, and I'm using cloud resources to compile it. So I'm getting super fast compile times because I'm using the cloud to do a load of the work for me. That work, that we're rolling that out over Epic at the moment. It looks like we're all on track to get that at least in a beta version. For you for 5.5. In fact, there's not a lot of technology there, like new bits of code that we need for it. A lot of it is about setup and giving you kind of what you would expect to see in 5.5 is a bit more of a blog post or a white paper, and sort of this is how we set up the relay mode, and this is how you can do it from working from home. But we are making sure all of our devs working from home are able to compile using UBA. We're going to be adding shaded compilation. That is already being used in Epic, so it's not just going to be limited to C++. It's going to be shaded compilation as well, which I know is it's a typical hot topic for iteration. We do the agent throttling, so yes, you will be able to install this on an artist machine, and then when Maya's shut down, you'll be able to use it, or at night time, you'll be able to use resources that are kind of that are sitting around maybe in your office or whatever to do compiling and come online and do things for you. We're going to have support for Mac OS and Linux. We know Epic is looking at shipping Fortnite on iOS later this year, and so we're ramping up our our fleet of Macs that we can use for this. So that's another cool thing, the support for Mac and Linux. And there's going to be a bunch of other UX improvements with it as well. So let's talk about editor iteration. So this is with Unreal Zen Loader. So Unreal Zen Loader is our new loading path. We've had a whole bunch of loaded paths in Unreal Engine over the time, and we've got at least 4 of them. But Zen Loader is hoping that we can reduce the number of load paths from 4 to 2, and that makes it a little bit easier for us to maintain. But it's also with a view to introducing async loading. We'll talk a little bit about that later on. But the Unreal Zen Loader in Editor, one of the big things that we want to do there is open up the door to async loading. So yeah, it was beta in 5.4, and it should be enabled by default. So we can say that's production ready if it's enabled by default in 5.5. So one of the things that we've been doing with editor iteration over the last sort of 6 months is we've been looking at reducing the time to play in editor, because that is a long pole of like developers' days, just booting the editor, getting into loading a map and getting into Pi. So we've been really focusing down on improving that Pi iteration. So the way we've done this is we've built a bunch of editor performance tests. So every day we're able to boot up Fortnite, City Sample, Ancient Game, and track that time that it takes to load all of that to Pi. And we're using Unreal Insights to look for like low-hanging fruit, looking for problems. And more, we're going to talk a little bit about telemetry analytics in a bit, but we've been using, Unreal telemetry and analytics to track performance over time, so that we can see where the problems are. We see there's a problem, we use insights, figure out where it is, fix it, put it into the code base, and then we can see how we're improving over time. So you might want to ask, we'll ask that in a minute. So in terms of what we're measuring the initial time to boot in editor, the time it takes to load the map and for the editor to be usable to actually go into Pi, that first Pi transition, which is often quite a long time, and then the time it takes to shut down. So that all gives us our time to Pi. So we're focused on these KPIs. We get the telemetry for it. We use this as our yardstick. And we'll look at the low-hanging fruit. So it's not like major re-architecting of the loading system, but there is a lot of low-hanging fruit. So how did we do? 44% reduction in that initial editor boot time on Fortnite. So that was a pretty good return. And a 23% reduction in that transition to Pi. That's all just from low-hanging fruit, things that were hanging around, legacy code, things that were, that were easily improved. So there's still a bit more mileage in there. I don't know how much longer we'll keep on with this, because eventually we'll get diminishing returns, and there's some more exciting things that we want to do with the loader that I can talk about in a bit. So that's all the stuff that you can use and try today in 5.4. And this second part here, and be very conscious of time. The next part here is like what we're going to do next, how we're going to build on the stuff we put in 5.4. So what I want to get from these kind of talks here is for you to see what's in the box today, what's coming up, and we'll continue to keep moving things from the what's coming up box into the current box, and hopefully you'll come on that journey with us, and it won't be like you'll be waiting years and years for this. You can start, you start getting the stuff I've already told you about up and running, get familiar with it. And then when you get to like 5.5 or 5.6, we're going to introduce some additional pieces on top of this that build on top. So I talked a little bit just now about telemetry and analytics and how we use that to improve our editor load times. I've got this vision for telemetry and analytics. I think teams should always know what their health of their team is like, right? Their developer efficiency of their team is like. We get a lot of anecdotal, I've just booted the editor, it's taken forever, oh, this is rubbish. And sometimes there's like, people are suffering in silence, right? It's like there's a whole art team that's sat there and their load times are just appalling, but nobody's saying anything because they just think, I don't know, even if I say something, no one's going to do anything about it. And, there's these kind of people laughing in the front. You know what I'm talking about. So we want to make sure that there's good tools so that you've got a good way of knowing how your team is doing, how long the cooks are taking, how long the editor's taking to load, how long people are spending going into Pi, how hitchy Pi is. Because if you don't have a good picture, you don't know what to tackle, right? You need to be able to get something that gives you that information quickly and allows you to act on it immediately, Teams should be able to act fast. And I also want to make sure that the common things that you all care about, especially the stuff which I care about, which is developer efficiency. I want to make sure all those workflows and all those pain points are covered out of the box. So you don't have to go into engine source code and annotate everything. You don't have to annotate the cook. You don't have to annotate your compile times. You don't have to annotate load times. That should be out of the box. You shouldn't have to subscribe to any analytics system to get this benefit. And you don't have to be locked into ours either. You should be able to use whatever you've got already. So teams that use Grafana, Splunk, whatever, they should be able to use the same, at least use all the same annotation and hook it into their own existing analytics systems. And if you don't have any of those products, you should be able to get that for free from Epic. So that's the vision. So this is typically how we deal, well, certainly how I've seen developer efficiency dealt with. I don't know, does this ring bells with everybody else? You kind of, over a course of a year, it starts off all right, and then it gets gradually worse and worse and worse, and then maybe after about 3 or 4 months, it's like everyone's on fire, and there's a massive effort. Everyone jump on, fix the load times or fix the cook times. And you do that, everyone jumps on, Ray, we're all good again, and then the whole process starts again, and then another 6 months. Is that right? Yeah? Yeah, okay. And so what we really want is we want to get to this bottom thing where we're just doing this incrementally. So you don't really see a massive step reduction in efficiency. You're able to keep on top of it. But for that, you need really good analytics and good tests and stuff like that. So that's part of this vision here. It's all right me telling you, this is how you improve developer efficiency. You use all these features, and you got good developer efficiency, but suddenly it tanks for some reason. It only takes someone to check in one line of code to add 20 or 30 minutes to your cook time. You need to be able to get on top of it, know it's happened, nip it in the bud, get that thing backed out, get the person who put it in to change it. Otherwise, it's, you're back to that death by 1,000 cuts thing, in 6 months' time. So just some quick terminology. So what I call telemetry is that captured application state, which is sent to an analytics system as a series of events. Metrics are a kind of resampled or downsampled version of those raw events. So a raw event might be editor load time or editor time to Pi or whatever, number of trees cooked or whatever. A metric is where you boil that down. So it'll be the editor load time for a particular stream over the day, the number of trees in a particular level over the week, that kind of thing. So that's a metric. An analytics provider is something that's a bit like a driver, essentially. And so the idea of that is it takes those raw events in on the client side, and it allows you to send those to an analytics backend or an analytics system of your choice. So this is where you can intercept all those raw events coming from the engine and get your, add your Grafana or your open telemetry backend or whatever it is that you currently have. If you write out to files, that's fine. You can write a file thing here. In fact, in the box, there is a JSON stream analytics provider provided as a sample. And then finally, you've got your analytics system. So this is the thing that will process the events, generate the metrics, report and visualize all of that data. So for 5.4, we've got an experimental plugin. It's called Studio Telemetry. You should be able to use all the existing events that we've added for developer efficiency. You should easily be able to add your own. So within your own products, you should be able to just add Studio Telemetry, add event, blah, 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 blah. And so you can use this to annotate your own game in whichever way you want it to do. All of that goes through Studio Telemetry. Licensees can write their own analytics provider, so you can write your Grafana one, you can write whatever it is you use for your own telemetry system, and obviously your licensee's analytics system and metrics, they're all your side, but this is where you get in, you put in an analytics provider of your own, and then you could use that data. However, if you don't want to do that, we've got what we call Unreal Horde Analytics Provider, and as its name might suggest, it sends analytics to Horde. So if you're using Horde, or again, just want to be really clear, Horde isn't just a CI/CD system, right? So if you're looking at Horde and you're saying, well, I've got TeamCity or I've got Jenkins or whatever, that's fine. But Horde, you can use it for remote execution for C++ compilation with UBA. You can use Horde for analytics. So if all you use it for is analytics, that's absolutely fine. Spin up a Horde server and you can get your entire team to start sending data back to Horde today. So some of the things that Horde Analytics provides, we've got support for multiple tabs, filtering, selectable time ranges, timeline charts, bar charts, a whole bunch of things that you'll find in most things. And there's like example dashboards for things like DDC, which is I've been talking about quite a bit today, cooking, editor iteration, and there's also a UBA one now as well. So you can actually see how well UBA is doing, how it's distributing, how many actions are being done, what your compile times are for various parts of your project. So we've got the whole, pretty much the whole end-to-end of where you might have problems with developer efficiency kind of covered already, apart from interaction with source control. But that's something that it's really useful for people to know how long syncs are taking or submits are taking, then that's something we can definitely add. So that's analytics. Wow, time. So back to Zen Loader again. We're looking at asynchronous loading on Zen. One of the reasons we want to do this again for developer efficiency and developer iteration is that editor loop, right? When you're in Pi, we want Pi to feel like as close to the game as possible, right? But it's not always like that. If you've got I don't know where it starts becoming a problem, but typically you can go and run in Pi. You've got a representative level from your game. You run around, you hit a tree. I'm talking about Fortnite here. I run around, hit a tree. Suddenly it's going off and baking a particle effect. The whole thing chugs to the ground. You wait, and then you carry on, and that just happens over and over again. And eventually, once you've hit enough trees, you get a smooth play. Does that sound familiar? Yeah, so that's why a lot of times artists and designers don't like using Pi. They're trying to test animations or gameplay loops, and then they're halfway through testing it, and then they tap a tree, and then it just sits there for 30 seconds. So that's one of the things what I'm going to call hitchless Pi. And that's like removing this blocking just-in-time work. So typically what happens when you hit that tree, you go off to the DDC. You go, have I got this texture, mesh, or whatever, or particle effect that I need? DDC goes, no, I haven't got it because I haven't got shared DDC. Another reason why you need a shared DDC. Or then it will go off and you go, I haven't got this thing. I'm going to go and build it. And then it goes and builds it. And that takes some time. But typically, there's still systems within Unreal Engine that still wait on the game thread for that work. So we're making a real conscious effort to look at async loading and removing all of these pinch points where systems wait, maybe a shader or materials waiting on the game thread for it to be ready, and to move more and more of this stuff asynchronous. So this all comes back to asynchronous loading, asynchronous access to DDC, shared DDC, virtual assets. All of these things will feed into, and even like UBA for shader compilation. So all of these things are feeding in to try and reduce the time it takes to generate this data on the fly, but also, making the whole system async. So even if you do tap that tree, it doesn't result in a massive performance spike. Maybe the tree takes a little while to appear, but it will never get it completely in parity with target. But certainly looking at getting rid of the hitches. And how are we doing that? So we've been testing it against City Sample, Fortnite. We get some really good progress with it. Really promising results. There's still a number of areas that are still causing us problems, things like blueprints. And then there is a ton of code that's just not thread safe. But believe me, I mean, it's going to be a good feature when we finally get to release it to you, but it is a bit of a slog, I will be honest with you, because there is so much legacy code and we need to make sure that's all thread safe. And how do we do it? We use a thread sanitizer system. So we're going to give you these tools. We're running a thread sanitizer pass. We're using those same automated tests we use for testing the loading and getting the loading performance. We're using those, running those with a thread sanitizer, and then looking at each one of those issues and weeding them out one by one. So it's a pretty laborious process. So I do hope you appreciate that we're doing this. However, that's not where the story ends. Even when we've gone through our own code, just to set some expectations, if you want to use this async editor loading for yourselves, then your own code needs to be thread safe as well. So we'll provide all the tools that we use, so the thread sanitizer stuff and everything. We'll provide those, but there is an expectation there that we're not magically going to be able to fix your async code or non-thread safe code, right? So you're going to have to do a little bit of work yourselves if you want to use this. Okay, nearly there. There's some more stuff we can do with improving cook time. So we've talked about, we're using Unreal Zen Server, and that's improving I/O and should help to us improve our cook times. The async loading actually helps us improve cook times, because a lot of what cooking is loading and transforming and saving, but we do an awful lot of loading. So improving load times and allowing for async loading will improve that. We've got multi-process cook. We've already talked about that. So loads of tricks already to improve our cook times. We're going to talk a little bit about incremental cook. So how many people have used iterative cook or cook on the fly? How many people trust it? What? No one? Oh, surprise. So yeah, incremental cook on the fly there. There is an expectation there that, if you can use it and it helps you, that's great. But, we're always going to hit a point where it's limited to what it can do. And a lot of the reasons for its kind of unreliability is that we're not tracking all of the dependencies that something that needs to be cooked, knowing all of the dependencies and whether to recook something. So we got things like, it's not robust code changes or asset changes or config changes. These are three typical things that change that, if you don't know that they've changed, you don't know whether you need to recook something. So with what we call incremental cook, and it's specifically named different because I want to set some expectations of incremental cook over iterative cook. And it's going to be 100% reliable. Now, you heard it, 100% reliable. The way we do this is there are a number of types in the engine that we can make incrementally stable, typically leaf types and the kind of big heavy hitters. So we're already looking at a lot of the heavy hitters here. And there will always be some types that they disappear into custom serialization functions or whatever. And you don't know what happens when they get cooked. So there's always going to be some types that we can't reason about reliably. And those will always be brute force cook. So incremental cook is everything that is incrementally stable, you can cook incrementally, and everything that you don't, you brute force. And the idea is that you gradually move the buckets from unstable to stable over time. So eventually, the hope is to get as near to 100% types in the incremental. So using incremental on the build farm is probably like that. The incremental works for local and for build farm. But one of the problems of doing an incremental cook on a build farm is that you need to, we don't persist state between runs. So build agents typically are ephemeral. Unless you've got the same, some teams might just have the same build machine and they use it all the time for their cooking. Certainly when we at Epic, we have, we're using a lot of cloud resources to do all of our build jobs on Horde. And so we never get the same build agent twice. So, we can't take advantage of the state from the last cook. So what we've introduced is, So we've already talked about writing cooked assets to Zen server. So our build jobs will write their DDC output to a shared Zen server. Our build jobs will write cooked assets to the Zen server. And we're also going to write this thing, what we call Zen snapshots, which is the rest of the state from the cook we will write to the Zen server. So that means you cook on agent 1, you store off all the cooked assets are already written out to the shared thing. You save the rest of the state in what we call a snapshot. So snapshot is just essentially metadata and a bunch of references to cooked data. Some other bits and pieces that allow us to do things like dependency analysis and so on are written to that. You save that out to the shared Zen server, and then the next time around, the next cook job that comes along pulls that, and it uses that as a starting point. And we can also, just like with the cooked assets, we can distribute those with the cloud as well. So if you've got the cloud part on there, you can distribute Zen snapshots around the world as well, which is pretty cool. And that leads us into the very last section, which is like, this is really putting everything together. So, we really want to, even though we're going to improve things like editor load times and hitchless pi, you sometimes always have to still go back to the target, right? One of the biggest bottlenecks with iterating on target is, well, first you've got to cook. If you change something, you've got to cook it all. So hopefully incremental cook helps you there. We can actually do a fast local incremental cook. And then it's actually copying that data from the PC to that target device. And that's actually can be quite a long time. Is that taking people a long time? Copying over to target? Not a problem? Is a problem? Because if it's not a problem, we won't bother. Hopefully it's a problem. Maybe you just don't do it because it takes so long. So this is our legacy target iteration. So you might use cloud DC or you might use a shared DC. That's completely optional. Let's just focus on that core line there. You have your source assets, you cook, you write a load of cooked assets to loose files, you write a load of DDC to loose files. Then you run Unreal Pack, that generates this big chunk of pack files, and then you copy all of that over to your target, and then it's only then can you actually test it. So that whole process is quite a long, laborious thing. If you've only changed one mesh, you've got to do all of that. So what we're going to do is, as we said, we write in cooked assets to local local Zen server. What we're going to be able to do going forward is those cooked assets, we're going to be able to stream those directly to client. So we're removing that bottleneck of the copying, and we're streaming it directly to client. This means that there might not get the same I/O performance as if you'd done it from target. But if you're iterating and testing things, maybe that's not important. Maybe I/O speeds are pretty fast, network speeds are pretty fast going to targets these days. It might be for the vast majority of cases where you're iterating on content on target that you can live with a little bit less performant I/O. If you're writing a high performance racing game that's streaming everything and you're right to the wire, then maybe you might see some problems with this. But by and large, we think this is going to be sufficient for most cases. And there is the option in the future to be able to cache this data as well. So we don't do this today, but being able to cache this cooked assets on the device as you're using it is something that we can definitely look at in the future. And then the final piece of the puzzle is, remember we talked about incremental cook and the build machines, and now we can pass the state from one build machine to another. Well, we can actually do that on the local machine as well. So when we're building this, the vision, what we've got for the future is artists comes to work, they go off and look at the builds from the nightly, they want to iterate on target, they go off to the build machine, they see there's a build from last night, they sync that cooked Zen snapshot. Well, they've already cooked the Zen snapshot from yesterday. They've already used the Zen snapshot from yesterday. So they're pulling that over Zen. They're only pulling the deltas, so they're just pulling down the things that have changed since yesterday's build to today's build. And then they've got some local changes. So now this is where incremental cook comes into it. We've got that Zen state. It's exactly as if your artist machine is now at the state that the cook machine was in at last night. And they've got some local changes, and this is exactly what happens with an incremental cooker on the build machine. They're only going to cook the things that have changed. They cook the things that have changed, and then they stream it directly to the target. So that is where hopefully you can see from here is how all of the pieces that we've talked about today are all going to fit together, and this is where we're going to go with full-on target iteration improvements and improve developer efficiency in the future. Very quick summary, because we're nearly out of time. These are all the features we've talked about. These are all the ones that are in 5.4. You can see there their readiness. Get on and use them. So yeah, try these out today. Improve your efficiency with Zen Server for local and shared DDC. Get those faster load times with the Unreal Zen Loader. Set up Unreal Cloud DDC if you're globally distributed, and this is really important to you. Reduce your sync times, and you're not just, I also mentioned it's not just saving your sync times, it's also saving your disk space as well. So if you're buying very expensive SSDs and drive space is a premium for you, then using virtual assets will help you with that. Speed up the cooking with multi-process cook, and go and distribute your code builds today with Unreal Build Accelerator. So there's all things that are in the box today that you can go and try. And then looking beyond that, this is where we're going with it. We're going to have that async loading in editor, hitchless Pi with Unreal Zen Loader. We're going to get this faster target iteration and build deployment with the Zen server. We're going to get faster cook times with incremental cook. We're going to give you the tools so that once you've got all this massively improved workflows and better efficiency, we're going to give you the tools to make sure that it continues, so that your teams aren't just throwing in things that suddenly tank your cook or make your builds longer. So you can keep an eye on it for yourselves. You can know you can get a feeling of the heartbeat of your team and how their developer efficiency is. And then finally, we're going to allow you to distribute your shader builds with Unreal Build Accelerator, and we're going to let you do Unreal Build Accelerator from home as well. So it's all really cool stuff that's coming. Some of that is going to be in 5.5, and some of it will be a bit later. That's it. Thank you.